Hello everyone, and welcome to part 7 of my VR Weapons tutorial. I had originally planned to deal with throwables, but as we've covered most of this in our object interaction tutorial, it would be double. Instead, we're moving on to projectile weapons. In the next few parts, we'll look at implementing the sniper weapon being displayed in the background. With a sniper rifle, we're shooting at targets over a longer distance, and the instant hit registration we get with a raycast doesn't fit anymore. Instead, we're going to have our bullet represented by a rigid body. This results in a far more realistic simulation, with the bullet losing height as it travels through our world. However, due to the size of a bullet and the speed at which it travels, we'll run into some interesting issues. Now, we won't repeat a number of things we've handled earlier on in the series, such as keeping track of ammo and reloading our weapon. But we will add a few new tricks, such as a functioning scope and using our second hand to stabilize our gun. Having a look at our project, we see that a lot has changed. I've taken a bunch of things we've covered in other tutorials and applied them to this project. We now have a simple scene selection which loads the chosen scene in the background, and as you can see, there is a new scene that provides us with an outdoor environment much more suitable to our sniper. I've also updated the project to the new XR Tools library and the latest OpenVR plugin. As this would result in going over a lot of material again, I'm skipping over all the work done here and will go straight into implementing our sniper rifle. If you're interested in the process, I've started live streaming my development sessions when I need to do work such as this. I don't have a live streaming schedule yet as I'm still getting my bearings, but follow me on Twitter where I generally announce when I plan to stream. Last but not least, I'm now capturing my tutorial footage with an Elgato capture card, which I was able to purchase thanks to my generous Patreon supporters. I'm hoping this will improve the quality of the visuals a lot, though I'm still experimenting with getting the settings right. So let's start with creating our sniper rifle, and for this I've downloaded Kenny & L's Weapons Pack. Here you can see all the weapons loaded into a simple scene just for display. There are all sorts of weapons, but we'll be using his sniper rifle model. We start by creating a new inherited scene, and the scene we want to inherit from is our object pickable scene in our XR Tools library. We'll rename our root node Sniper and save our scene. We create a new folder to store all our sniper rifle scenes into. Next, we'll extend our script on our root node so we can add logic to this. Just as a placeholder, we'll add in our action function. This is the function called by our pickup logic within our VR setup, if we pull the trigger on our controller while we're holding our gun. We first add a spatial that we'll use as our pivot point. We won't be using this for our recoil effect like last time, but we'll use this for our two-handedness later on. Now we add our mesh instance for our gun, but we start by creating this on the root node. We'll rename that node to gun. Now we load in Kenny's sniper rifle object. Our gun is facing the wrong way, so time to turn it around. Next, I'll quickly add another mesh instance, and we add a cube mesh to this, which we size to the length of 1 meter. We don't really care about the other sides. We move this back a little. Now we resize our gun so it's similar in size. It doesn't need to be exact, but according to Google, 1 meter is a good ballpark for the size of a sniper rifle. Now we can remove our cube. We're going to move our pivot point to where our grip is. Doing so showed us that our gun isn't perfectly centered, so we'll go to our top view and adjust it a little. Now we can make our gun a child object of our pivot. Next, we add a spatial that will position at the front of our muzzle. This will become our spawn point for our bullets. We'll add an export variable to our script that will allow us to set the scene will spawn whenever we fire a bullet. Before we create our bullet scene, let's name one of our physics layers as the layer we'll use for our bullets. We'll create a new 3D scene and change the type of our root node to rigid body. We'll name this bullet. We'll add a mesh instance to represent our bullet and create a simple sphere object. Our bullet will be moving much too fast to see any detail. I'll make it slightly on the large size so we can more easily see it when we test things out. We also need a collision shape and give it a sphere shape that matches our mesh. Now we can save our scene and we'll place it alongside our sniper scene. I also almost forgot to set up my collision layers. We place our bullet in our bullet layer, and we set our mask so our bullet hits anything in our environment or any of our other objects. Now we can assign our bullet scene to our sniper. While we're here, we're also going to assign our sniper mesh to our highlight setting. This is a new setting on Object Pickable that automatically applies our highlight when we're able to pick up our object. We are also going to add a spatial that will allow us to define our pickup point. We'll place this in a bit of a weird spot, and this takes a bit of experimentation, but it's actually the top of our controller, and our hand that holds our gun will end up somewhat below it. We also need to add a collision shape to our gun. We'll use a box shape and just size it so our gun fits nicely inside. I'm decreasing our margin a little because it's very close to the width of our collision shape. Time to make our gun shoot, so back in our sniper script, we'll implement our action function. We do want to have a cooldown, so we'll add a can shoot variable. Now we add a timer to our scene for our cooldown. We're not doing animations for our reload and such, else we could use that just like we did before. This time, we'll just implement our timeout signal and simply set can shoot to true. Then in our action, we check if we can shoot. At the end, we'll change our can shoot to false and start our timer. We'll instantiate a new instance of our bullet scene. We better also check if our bullet scene is set. Now we need to add our bullet to our scene, but we're going to add it to a container node on our main scene. I don't really like hard-coding paths like this. You'll see how easy it is to type this in wrong, and if we ever change our main scene, we'll be in trouble. But for now, we'll use it directly. We can now set the starting location and orientation of our bullet by assigning its global transform to that of our muzzle node. Finally, we set the linear velocity of our bullet by using the inverse of the z-vector of the basis of our global transform. Oh, that's a mouthful. We do want to multiply this with the speed at which our bullet will travel. For this speed, we'll add an export variable so we can tweak it and set this to a ridiculously low value for testing. We add our sniper scene into our outdoor scene and position it just above the table. As mentioned, I got the path to our spawns node wrong, so let's fix that up. We can pick up our gun, and we see that we can nicely fire our bullets. They immediately fall to the ground, but they work. Our cooldown timer is a bit high. Let's lower that to something a little more sensible. We'll also change the speed of our bullet to something a little more realistic. A quick Google search gave me a figure of just over 300 meters a second. So that will do for now. Every time we shoot, we add another bullet to our scene. They will land somewhere and just roll around forever. Let's limit that by adding a lifetime timer to our bullet. We do need a script for this. We'll leave our timeout on our bullet at 1 second. We make sure one shot is selected. We also want to start this automatically. Now we hook our timeout signal up and simply cue free our bullet. Now we need to react to when our bullet hits something, and for that we hook up our body entered signal. Here we check if the body that we hit has the hit method implemented, and if so, we will call that method and pass it our bullet's current position. We also cue free our bullet at this point. So testing our work so far, we can see our bullets travel really fast, but nothing happens on the targets. Let's do something about visualizing what is happening. Obviously, this part is only for helping us and not code we would normally add into a game. But we're going to add objects into the scene on each call to our physics update method. We start by creating a new mesh instance object. We'll add an onReadyVar to get our main scene spawn node. And we add our new object to our spawns node. Next, we copy our global transform. We also want to give it a different material to make it really visible. So let's add an export variable as a helper for this. We now need to assign this material to our first service. We do need to assign our bullet mesh to our new mesh instance. We can now assign a material to our bullet node. We just use our highlight material from our XR tools here. Last but not least, we won't get any hit registrations if we don't turn on contact monitor on our bullet node. We also want the number of objects we report on to be at least 1. This time I didn't forget to go full screen. Now when we shoot our gun, we can see how our bullet travels through the world. Our physics engine is set to update the position of our physics objects 90 times per second. The distance between our blue spheres is the distance our bullet travels in 1/19th of a second. Each physics frame, our physics engine will move our object to its next location and then check if it is colliding with anything. As we can see, our bullet never collided with our target. One frame it's in front of it, the next frame it's behind it. Now the obvious fix for this, according to the documentation, is to turn on this setting called continuous collision detection. This will tell Bullet not to just check if our bullet collides at the position it's moved to, but to perform additional collision checks along that path. And so we turn this on. It still didn't work. Now we're not showing here what continuous collision detection does. We're still only seeing where our bullet was every frame. I'm not sure what the exact setting is, but Bullet will check our collisions in a number of steps. So say that we have 4 checks in total, we're still very likely to skip over our target, which is exactly what is happening here. There are a number of ways to solve this. We could go down the same route as we did in our interaction tutorial and increase the physics update frequency. Setting this to say 180 frames would double the steps we're checking, and together with continuous collision detection, our gaps might become small enough. Increasing the thickness of our collision shape on our target would help as well. But there is a better fix. We start by turning our continuous collision detection off again. We won't need it with our fix. Next, we're going to change our collision shape to a capsule shape. We'll size this down to our bullet size as a starting point. We are also going to turn on local to scene on our collision shape. If we have multiple bullets flying around, we want each to have a unique collision shape, as we'll be modifying it. We're going to add a function to our bullet script and move our mesh instance creation script into this. We'll call this method from our physics process. Next, we're going to replace our bullet mesh with a new mesh that will create on the fly. This could end up getting different settings for each instance that we add. We create a new capsule mesh. We'll set its radius, and we copy the height from our collision shape. Now we assign it to our mesh instance. We'll add a new variable that tracks the position of our bullet so we know where it was in the previous physics frame. And because we want our starting position, we'll add a function for this. The problem we have is that when we add our bullet to our scene tree, we haven't set its global transform yet. We also create our first test object here. In our physics process, we now grab our new position from our global transform. We then calculate how much we've traveled and update our last position to our new position. Now we use our delta position to determine how far we've traveled, and we update our collision shape to be that long. I'm subtracting 1/10 to account for the capsule shape's radius. We're making sure our collision shape covers the entire distance we travel in one physics frame. I'm also clamping that value to make sure it doesn't become negative. It is important to realize that we're setting the size for checking the collision on our next frame. Seeing, however, that we're unlikely to slow down by any meaningful amount, this is not an issue. With that done, we go back to our sniper script and call our setStartTransform method. Now when we shoot, we still don't see our bullet hole. We'll come back to that later. But we can see that our bullet trail ends as we hit our target, so our collision detection worked. That said, if we look at where we start, we see that our first collision shape is very small, and there is a big gap. First, we're going to make our shapes that visualize our collisions a little thinner. This will make it easier to see if our bullet holes work. Spoiler, they don't. Not yet. We get our first call to our physics process when we haven't moved our bullet yet. We're going to check if our position has actually changed. I'm removing our test object in our setStartTransform function. This will turn out to be a mistake, but we'll get back to that later. We want to calculate the correct starting size of our collision shape so that we're checking the correct collision from the start. We can calculate how far we'll travel in a single frame by taking our linear velocity and dividing that with our physics frame rate. I'm calling this guess travel because we're not taking our gravity and potential collisions into account, so it's a pretty accurate guess. We can just copy our collision shape formula from our physics update and change it to use our calculated value. Sorry, I forgot to go full screen again. We can see that our collision is still detected, but there is no bullet hole. Let's test an up-close shot. We can see our collision fails, and I initially drew the conclusion this is due to the collision not being tested in the first frame. But when we shoot from slightly further, we can see that we again have an accurate collision detection. Finally, shooting from pretty much head-on, hey presto, we have a bullet hole. The reason our bullet point is positioned wrong is that we're using the position of our bullet, not our collision shape's intersection point. So to solve our first issue, we change our starting point so our collision shape nicely covers the correct distance. As I believe our starting collision isn't checked, I simply moved our starting point back by half the distance we travel in one frame. I'm making another mistake here, and that is that I forget to move the code that assigns the transform. I changed that off camera. Now you can see our first shape nicely starts at our muzzle, but notice how our objects don't nicely line up. But before we get into that, let's first fix our bullet hole. Note the fix in our setStartTransform function where I've moved the line of code that assigns our global transform. In order to reposition our bullet hole, we're going to need to tell our hit function the direction of travel of our bullet. We simply give it our linear velocity. In our hit function, in our target script, we'll add our direction as a parameter. As we're doing everything in local space of our target, we need to apply an inverse transform to our vector, but seeing this is a directional vector, we call this function on our bases. Just to make sure our raycast logic doesn't break, we should add a default. And then only do our adjustment if our direction vector has a length. The x component of our hit point tells us how far in front or behind our target we are, so we can simply use that to move our hit point along our direction vector. We do need to normalize our direction vector for this to work. Okay, this is weird. Our first bullet hole is spot on. Our second bullet hole is off center. And our third is missing. I don't have a good explanation here, but it turns out that sending our linear velocity doesn't work. My best guess is that we're setting it as a global vector, but once the physics engine takes over, it becomes a local one. Anyway, easy to fix. We're calculating our movement already, so all we need to do is remember that by making our delta velocity a script variable. And then we send that to our hit function. Now when we shoot, hey presto! And then it doesn't work. It almost does. So, the reason for this is that as our bullet travels and gravity pulls it down, its heading slowly changes. But the orientation of our bullet does not. So we're going to take control of the heading. We use our lookAt function to align our bullet to the direction of travel. As you can see, I've shot at our target a bunch of times. We notice that our bullet holes are now on point, but we also notice something weird going on with our trajectory. It turns out bullet does check the collision of our object at its starting point. We moved it back, and now when we fire, the collision shape interacts with our player and gets a small nudge. That gives it a small angular velocity. So we need to move our starting position forwards instead of backwards. I thus also want to put our visualization back into place so we can see what is going on. And finally, we use our calculated travel for our first frame as our first frame delta position. Now when we shoot from a distance, we see that everything is spot on. We get a nice smooth trail and our bullet hole is right where it should be. When we hit the target up close, we see that our collision detection still works, but our bullet hole is slightly off. I think this last one has something to do with us using our starting linear velocity, but I'm happy about the results so far. Even hitting our target far away, we can see that our collision is spot on. This is where we'll leave it today. In part 8, we'll continue with our sniper by making the scope work. Don't forget to subscribe so you won't miss it. If you found this video useful, I would really appreciate a like. Please consider supporting me more directly through Patreon. And follow me on Twitter where I post frequent updates. See you all next time!